Okay, in the exam guidelines, there are some electrolytic cells that you're supposed to know the exact process for. So we're going to have a closer look at them. Amongst them is the one to produce tin foil, which is actually aluminium foil, or JIC. Remember, we've talked about this, the chlor-alkali process, when we're talking about bleaching hair and stuff. So we're going to talk about this again. Or, for instance, electroplating. These are spoons that have been electroplated. You can see by the stampings on the back exactly what happened to the spoon. So there's supposed to be the decomposition of copper chloride, which I've shown you in real life. We need to discuss how to electroplate an iron spoon with silver or nickel, how to refine copper, the chlor-alkali industry, and then how to get aluminium metal out of bauxite, okay, which we actually import from Australia. And then we need to know why the chlor-alkali industry is bad for the environment and why it is bad for the environment to get aluminium metal from bauxite. So let's go through all of these different reactions. So what do we use electrolysis for? We use it to get out some non-reactive metals or metals that are hard to purify, like aluminium, magnesium, sodium, and gold. So we can only get like that chunk of sodium metal if we use electrolysis, because it would far rather be a sodium ion than sodium metal. So we pump energy in with electrolysis and get out sodium. We also use it to get halogens like chlorine or bromine, mostly chlorine, because we've got quite a few industrial uses of chlorine. You can also refine copper and zinc. They also don't want to come out of their ore without some help from electricity. In the chlor-alkali, we also need sodium hydroxide, which is a major component of soap. And obviously, we need hydrogen gas as well, which is one of the feedstocks for the Haber process. And obviously, we like the Haber process to make ammonia, to make ammonium nitrate fertilizer so that we can grow crops. So the first thing you have to know about electrolysis is that you always have to use direct current. If you don't use direct current, the anode and the cathode are going to switch. So with DC, the anode will be positive, the cathode will be negative, okay? So this process uses really a lot of electricity. So anywhere where there's refinery, an electrolytic refinery, there will be massive power cables going in. And then on site, they will convert the alternating current to direct current with a rectifier. And then that's how this works. It's not like some teacher in their classroom with a little 1.5 volt battery gaily making copper. No. This is a very large, involved chemical process. So the first one we're going to look at is electroplating. So what usually happens is you get a cheap metal like iron or something. Okay, that's easy to get out the ground, easy to extract. It's got nice properties like you like. It doesn't bend, it doesn't break, it's strong, but it has other issues like it rusts or it's ugly or whatever. Okay, so in electroplating, can you see we've got a source of energy? We're using electrical energy to make a chemical reaction. So we get the cheap metal and we coat it with the expensive metal, a very thin layer. So it can prevent rust, for example, on iron, or it can improve the appearance, for example, with zinc. Okay. So now what's interesting about electroplating is that there are two half reactions. Okay. And the half reactions are coming from the same metal. So in here, for instance, if we want to silver plate this spoon, you actually have a silver nitrate solution, which gives you Ag plus ions. And then what you do is you hook up to the battery a chunk of silver metal. And then when you turn the battery on, electrons go to the spoon becomes negative, the silver ions go to the spoon, they accept the electrons and they become silver metal on the surface of the spoon, and the spoon starts getting coated in silver metal. But obviously, as you suck the silver ions across here, the solution is going to get depleted of silver ions as they're all becoming silver metal on the spoon. So you have to replace them in the solution, and you replace them in the solution by putting a chunk of raw silver metal in as the other electrode. So electroplating, this also happens on like your gold jewelry, like those cheap gold earrings you get when you get your ears pierced. They look gold when you buy them, and 5 minutes later they're all a funny stainless steel color because all the gold plating's worn off. So this is how it works. The anode is pure silver and the metal has to be plated as the cathode. You should remember this. They like to ask you which one's the cathode. So in the electrolyte you have silver nitrate and potassium cyanide. Okay, so the potassium cyanide just helps the conductivity, but the potassium cyanide is not going to do anything in the chemical reaction, but it helps the ions move freely in the electrolyte to get from the silver anode through the electrolytic solution to the cathode. So at the anode, the silver forms silver ions. Okay, they go into solution, and obviously now as this happens, the anode gets eaten away. So the big anode of pure silver metal gradually becomes into solution, goes across the solution, and ends up plating the spoon. So the silver ions in solution move to the cathode. They grab some electrons that came out of your DC power supply, and then they deposit on the cathode. So long as the cathode is something that the electrons can stick to, you will get a layer of silver. And then the cathode is obviously going to get bigger because you're putting a metal on top of what was already there. So look, it's exactly the same reaction, but at the anode, it's silver going to silver ions, and at the cathode, it's going silver ions to silver metal. Okay? So you need to be very clear when you answer these questions. If you know that, like, for instance, silver is involved, you can't just answer silver. You have to check, do I mean silver the metal or do I mean silver the ion? And you have to specify silver ions or silver metal or silver the element, silver the atom versus the ion. You need to be clear in your mind which one is happening. So here's an example of what it actually looks like in industry. For instance, car bodies, the inside of cars are sometimes electroplated to stop them rusting, or those shiny chrome parts. So there's often like a conveyor, and it's hooked up to electricity, and then it's got one charge, and then there's an anode, the zinc anodes, and a zinc sulfate or something solution. So they ship the car in, they dunk it, they turn the electricity on, it gets coated, they take it out. And these are what the different acid baths would look like. And there's racks that come over these trays. And here's the finished product. These are little anodized screws. So often you see things these particular colors, and you'll know that they're anodized metal, like key rings and little knick-knacky things. When they've got this shiny silvery look to them, they've often been the result of an electrolytic cell. Okay, so the next thing is making chlorine, hydrogen, and sodium hydroxide in the chlor-alkali process. We've looked at this briefly. Okay, what are the problems with this? Well, chlorine is toxic. Okay, so it's a bit dangerous, you can't smell it. So fairly obviously, if you're in a factory making chlorine gas and you've got a leak, you've got the potential to harm people. Hydrogen likes to go boom when we mix it with oxygen, so that's also a danger. Sodium hydroxide, strong base, it corrodes stuff, and if it gets into the groundwater, you can't drink your groundwater anymore. So you cannot put a chlor-alkali plant in a residential area because it's insanely dangerous. So they're usually off in some heavy commercial area and a bit isolated because of all of the other health and safety restrictions. So it's really takes a lot of energy because they're not spontaneous reactions. Okay, so they pump in sodium chloride at a high concentration, and they pump out sodium chloride at a lower concentration, and then they've got this ion exchange membrane here, and if you can see, there's like little red things and little green things. Okay, and it will let the little red things pass, but it will not let the little green things pass. And the little green things are the chlorine ions, and the little red things are the sodium ions, but it also won't let water pass. Okay, so when you plug in your anode and your cathode and stuff, here are the little chlorine ions. They go over here and they lose their electrons and they become chlorine gas. Okay, and then on the other side, what happens is the water goes up to the electrode and gets split into hydrogen gas and hydroxide ions. And then the hydroxide ions, because these little sodium ions from the salt water that you pumped in this side, so because the little salt ions can cross the membrane, because it's a very special membrane, because the sodium ions cross, they meet up with the hydroxide ions that are left when the hydrogen gas comes off, and then you pump out sodium hydroxide at the bottom. So the brine goes in, the brine goes out, the water comes in, the sodium hydroxide comes out, and in the meanwhile you're getting chlorine and hydrogen. It's quite a complicated, delicate process, this one. So if you have a look, okay, we have an oxidation half cell and a reduction half cell, and they're separated by the cation exchange membrane. So the cation exchange membrane only lets the cations through, and in this case the cations are the sodium ions. So they can go from the oxidation half cell to the cathode, but the hydroxide ions can't move the other way. They can't leave the oxidation half cell to go to the reduction half cell, even though they kind of want to go to the anode. Okay, they can't get to the anode. So what happens is these are left behind, and we pump the sodium chloride in, and at the anode the chlorine ions go to chlorine gas. At the cathode the water turns into hydrogen and hydroxide, and these sodium ions cross the membrane and they end up leaving as sodium hydroxide by bonding with these hydroxide ions from breaking water. And the net reaction is 2 sodium chloride plus 2 water goes to hydrogen plus chlorine plus sodium hydroxide. Imagine every time we dissolve table salt in water we got hydrogen and chlorine gas out. Nay, never, it's not happening. So you can imagine they must really put in a lot of energy and do some fine tuning to get this reaction to occur. Okay, one of the other reactions is the electrorefining of copper. So here you have a copper cathode and a copper anode, okay, but your anode is a big chunk of impure metal that you got out the ground, okay, and at the cathode you've got start out with a very thin pure chunk of copper, and then you let, when the anode decomposes, you then let this cathode build up more pure metal, and eventually you pull out a whole pure chunk of copper metal. And obviously you need the metal in a solution of its ions, so the copper goes in the copper sulfate solution. And then as this impure metal breaks down, it leaves behind some sludge or mud, which is stuff that can't react, that is exactly what you're trying to get out of the copper. Okay, so the impure copper is the anode. We acidify the copper sulfate. The acidification just helps with the ion concentrations and makes the electrolyte work better. The very, very thin pure copper plate is the cathode. The copper anode goes into iron, so it goes from copper metal to copper ions. And remember, we need a source of electrical energy to make this happen. So then the copper 2 ions move from one side of the electrolyte to the cathode. At the cathode, they get reduced, okay, they accept electrons, and copper metal is deposited on the cathode. And then what happens is, if there's silver, gold, platinum, stuff like that, often is impurities with copper in very, very, very small amounts, okay, they sink to the bottom of the anode. Remember, you can adjust the electricity so that none of these react. If you change the voltage into the cell, you will only allow enough energy in to allow certain reactions to occur. So silver, gold, and platinum sink to the bottom, and then you can take this anode silt out and you can sell it for somebody for silver, gold, and platinum. They refine it again. So you've got your pure copper product, and you've also got these byproducts of silver, gold, and platinum in very small amounts. And this is what the sheets look like, okay? So these are preparing, I think, to go, or have just come out of the electrolytic cell. You can see it's all wet and slushy from the electrolyte. And this is the metal conveyor that will have dunked them in. And you can see they're this nice shiny copper color, and they're stacking them to sell for transport. Zambia is big into this, and sometimes you see the big Zambian trucks shipping leaves of copper like this on the back of the truck, and the truck looks really empty because the copper is so heavy. Now the last thing we have to look at is the extraction of aluminium. Now this is the huge energy eater. This is why tinfoil is so expensive, and why tinfoil is so thin, and why half of the tinfoil is not actually tinfoil. So tinfoil is actually aluminium, and you have to electrolytically reduce the ore bauxite, which is aluminium oxide. Aluminium deposits are rare all over the world. We import our bauxite from Australia. So they get the bauxite and then they crush it and they treat it with concentrated sodium hydroxide. And then you get this pure alumina. So the ore is aluminium oxide, and this looks like the aluminium oxide formula. But you want to change it slightly with the sodium hydroxide to get this alumina. And this is like made at the electrolysis place, and you get red mud out of it, so that when you make the alumina you get some red mud waste. Okay, and the red mud is because there is iron impurities in this bauxite ore, and the iron impurities make red mud, which is dangerous, and it goes into big, what they call tailings dams on the mine. Whenever they store dirty mine water, they call it a tailings dam. So this is the setup. We've got a negative and a positive, okay, and they use carbon anodes, like those graphite anodes that I showed you, but obviously giant industrial ones. And then what they do is they also use carbon as the cathode. So the carbon is the anode here, the carbon is the cathode, and they've got this massive container where they melt the aluminium oxide, the alumina, and then they've got the carbon on the lining. And because they have to heat it up, because you can't put the aluminium oxide in solution with water, so to get the electrolysis to occur you have to melt it. It gets done in a steel tank which is lined with special bricks. Okay, so you have to put a really strong current through the alumina. It's really high, it's not very economical, but you can melt it. Okay, so you add cryolite, sodium aluminium fluoride, look at these, sodium aluminium and fluorine all bonded together, and then it melts at the not very low temperature of 950 degrees, but it's lower than the alumina melting point. Okay, and then you take the aluminium oxide in its liquid state and you split it into liquid aluminium and oxygen gas. So the steel tank is lined with carbon. The carbon's the cathode, the lining is the cathode, the electrodes in the middle are anodes. So when you make this oxygen at the anode, it actually basically catches fire. It combusts with the carbon anode and burns off its carbon dioxide. And the aluminium that's left behind sinks to the bottom of the cell, and then you drain it off. So if you've got the aluminium, it will replace the carbon lining as the cathode in due course. Okay, so aluminium 3 plus gains 3 electrons, becomes aluminium metal, oxygen ions become oxygen gas, and you get a complete reaction like that. Okay, so it uses about 3 to 5 volts. That's not a lot of volts, but look at the amps. 100,000 amps. Remember when we did our electricity reaction, we were using milliamps. Okay, we had 5 volts coming out the battery, but we had like 0.3 milliamps. This is 5 volts and 100,000 amps. It's an enormous current. Remember, the current is carrying the energy, so this is a really huge current, and this is really expensive. So always it's cheaper to recycle aluminium than it is to refine it, but you don't get enough aluminium to the refinery. But this is why stuff like recycling Coke cans is popular. And this is also why you should never ever waste tinfoil, because all the tinfoil you waste is destroying the environment, not only through the wastage of electricity, but also because of the bauxite mining. So don't waste tinfoil, people. Okay. You can't replace the carbon anodes very cheaply. They're expensive, so it's bad. And carbon dioxide is produced in this, and it produces a lot of carbon dioxide as the carbon anode burns away with the oxygen. And carbon dioxide is a greenhouse gas, so this is overall bad for the environment. The cryolite that you need to lower the melting point of the bauxite, it's also expensive. It's really noisy mining aluminium. There's air pollution. It damages the environment. And that red mud waste you mix with the creolite pollutes groundwater. So overall, tinfoil should be used sparingly, and all Coke cans should be recycled if you want to be a good person for the environment. So think twice before you throw out those Coke cans. And here are just some interesting extruded aluminium profiles. Aluminium gets used like for windows and around my whiteboard and stuff, and one of the reasons people still use aluminium is because it's really easy to push out of like a toothpaste tube type thing to make this extruded aluminium, and it's nice and light and nice and strong. So I leave you with this lovely image of extruded aluminium products, and look, you can see these have been anodized to another color.